So let's begin by writing down the analysis equation, which I have gone through in a separate set of videos on the Fourier series. So I would highly recommend that you review those videos and understand the maths there. I'm going to simply write down the equation here and really say very little as to its meaning or where it comes from, because that in itself requires a video, which as I've said, it has been done and it's on my YouTube channel. So the equation really consists of a signal x of t, and that's a good point because the equation, the analysis equation, of course, can be applied to any periodic signal, not just the rectangular waveform, but we of course are using it here to analyze the rectangular waveform. So let's just go through the equation and understand what it's trying to tell us. We have a signal x of t, which could be anything, and we're multiplying that signal with a set of sinusoids. And then we take the products of those multiplications and we integrate them, or you could say we sum them together to create an output. And so what we could say is that we are taking our signal, we are comparing it against something, a set of sinusoids, and seeing how alike the two things are. And in this way we are breaking our signal down into components so that we can have a different insight into the signal. Now the integration period here is shown from minus infinity to plus infinity, and I've really done that because we are dealing with continuous signals which theoretically extend from the beginning of time to the end of time, whatever that actually means. But in our case, we will not extend over such a long period. So actually, let's simplify things. Let's get rid of this extension of the equation, which we'll do anyway. But let's change the limits here. Keep the mathematics down on this slide. So we'll change the limits to cover basically one period. We are dealing with periodic signals because we're using the Fourier series, and the results are the same whether we use one or two complete periods to integrate over. So we've said that we are going to integrate from 0 to tp, but we can simplify things further because our rectangular waveform actually is only has a finite value over the period of minus 2 over 2 to plus 2 over 2, and during that time it has an amplitude of a, which is a constant, and it's multiplied again by the set of sinusoids. So we've shown that we've gone from limits extending from minus to plus infinity to a period, and then we've said we don't even have to consider the whole period because the waveform is only finite over a much smaller period. Let's take the constant amplitude out because it's not really a function of time. It's simply a constant. And now let's integrate. Integrating an exponential is of course simple, which is why we like exponentials. We simply begin by writing down the exponential as it was before integration. We then look at the exponent, which is this part here. We take the derivative of the exponent with respect to time, and then we divide our exponential with that result. So the result, of course, is minus j 2 pi k f naught, and of course this component was a constant, and the time variable disappears. Mustn't forget to put the a and tp on the outside, and we now will take the limits from well, the limits are 2 over 2 to minus 2 over 2. Now before we go any further, and the mathematics are going to get heavy, let's just let's say where we're trying to get to. So we really are trying to convert this equation into a form where we have the sinc function. And the sinc function is based on the sine function. And the sine phi, or if you have a sine phi, it's equivalent to writing down j e to the, oh, I'm getting ahead of myself, hang on, j to the power of j phi, mustn't forget the minus there, and then we have another minus j e to the power of plus j phi. And basically this thing here, if you divide by 2, it is the same as saying sine phi. It looks more complicated, but you know, it is easier to manipulate the exponentials mathematically than it is sines and cosines, so which is why we like this. But you know, what I want you to understand is I'm trying to convert what I have written down as my equation, the analysis equation, into this form. So I'm going to take this and I'm going to manipulate it so that I get something like this, and then of course from this I can derive the form which gives me the sinc function. So now that you know where I'm trying to get to and where I'm starting from, you should hopefully stay interested and follow the mathematics rather than trying to figure out where I'm going to and not really understanding. So we have A over the period of the rectangular waveform, and inside we now have e to the power of minus j 2 pi k f naught, and we're going to substitute for time with tau over 2. The 2's cancel, and then we divide by minus j 2 pi k f naught. We take the lower limit, so it's minus e to the power of minus j 2 pi k f naught. Time is now substituted for with minus tau over 2, so the minus that we have becomes a plus, and the 2's will cancel, and at the bottom we have minus j 2 pi k f naught. Okay. So we should notice that the second term has a minus at the top and the bottom, so we can rearrange things. So we have A over Tp, the period of the waveform, and we should look at taking everything else out as well apart from 2j, so let's do that now. So we're reforming the equation, and now on the inside we will have the second term coming to the front, because as I've said, it's got the minus at the top and minus at the bottom, and it simply gets it into a form which we want to get to. So e to the power of plus j pi kf naught tau, and then the second, what used to be the first term, is going to move and become the second term. Because of that minus in the denominator, we have minus for our second term, so it's e to the power of minus j 2 pi k f naught tau, and at the bottom we have simply minus j 2 because we've taken everything else and put it outside. Now it's in a good form. We could leave it as is, but I'm just going to multiply the top and the bottom by j, I think it should actually be minus j. Yeah. So now we look at this, and we start on a new line because it's going to be easier and hopefully clearer. So we just write what we had, and now look at the impact of this multiplication with minus j. Should put the second term now at the front because of the two minus signs. So we have this for the first term, and then for the second, because of the minus, we have minus j e to the power of j 2 pi k f naught. So we just rearrange the terms once more. And the bottom, okay, so we're multiplying two j's together, which will give us minus 1. Don't forget, the square root of minus 1 is j, and therefore j squared is going to be minus 1. So we've got two j's, so that's j squared minus 1 times minus 1, which is a plus. So we can write that down as a plus 1 times 2, but let's get rid of that and simply write down 2. It's neater. So I think this is the form that we want, because at the end of the day, don't forget, we're trying to get to the sinc function. And now we have a form which gives us a sine equivalent. So again, the outside terms stay the same, a over tp pi kf naught, and they are multiplied by a sine, because all those exponentials really just give us a sine, and the term inside is 2 pi kf naught tau. And now we should consider how we get this into the sinc form. And to do that, let's just remind ourselves of what the relationship is between the sinc function and the sine function by creating an area and writing down that the sinc phi is equal to sine phi over phi. Okay, so this is the form we want to get to, but let's just double check if you've got everything correct. And I think we'll do that on the next video.